Hi, this is Mark. Today we're going to talk about a recent report from the Particle Physics Project Prioritization Panel. Because of all the alliteration in the name of that panel, they call it the P5 report. It was released in December 2023. This report is designed to go along with the funding request for physics in the United States. It helps set priorities, set future directions, lay out the important priorities. So let's go through some of the report and see what we have to say about it. Before I get into the report, I just want to say, for those of you participating in the You Can Solve Nature series, this particular video is going to contain some medium advanced concepts in the new theory of point charges, the new ontology for the next era in understanding nature. So if you're on that track, you might not want to skip ahead to this one because you're trying to solve it yourself, and I think that's wonderful. If you can solve it yourself with a few clues, then you may have many new insights that I haven't had. I mean, there aren't that many people who even know about this yet, so you're one of the first. But let's get into the report. So I want to go through again what we're going to do in this video. I'm going to do a critique of this recent report from the physics and cosmology communities. It aims to align and justify their strategic vision with their future U.S. budget funding levels. And I'll do my best to describe three different perspectives on this report. One, it'd be my understanding of the consensus community view. I may not be right, but this is my understanding from following them, from listening to them, from reading the report. Then I'm going to give a view that I believe is the consensus of the concerned professionals in the field and critics of the field. And third, I'm going to give my view from the next era, looking back towards this current era of quantum theory and general relativity and lambda CDM for cosmology. Because while those theories have sort of worked, they also are at the wrong ontological level. And in many cases, the stories or the interpretations or the narratives of those ontologies is wrong, just wrong. And in other cases, it's off base. In some cases, it's right. So here's the cover page for the report. It's called Pathways to Innovation and Discovery in Particle Physics. It's also called Exploring the Quantum Universe. So they're trying to balance here particle physics and cosmology. Those are the two areas of interest for this report. This is the table of contents for the report. It's a 150-page report, goes through the recommendations, detailed chapter on deciphering the quantum realm. The fourth chapter is illuminating the hidden universe. That's on cosmology. Then they're going to go into exploring new paradigms, what they're trying to do in understanding particle physics and nature, how we invest in the future of science and technology, creating a technologically advanced workforce for particle physics. There's something they do in this report that I found a little bit unusual. They're trying to justify somewhere between a 2 and a 3% increase in the budget, but they don't really ever talk about what the current baseline is of the budget. I mean, you could back into it by figuring out what they're asking for and then, dividing by 2 or 3% to calculate the top line number. But I thought it was a little strange that the report doesn't do that. You can't never really tell the motivations of people when they write a report like this. It might be historical. I did look up what the number is. And if you look at the budget for the Department of Energy's Office of Science, which includes funding for high energy physics, it was $8.1 billion in 2023. So let's take a look at this chart and see if we can understand what they're trying to do. They're trying to cover the years 2023 to 2035. And they have different scenarios for what they're looking for. So what this graph is saying is that the amount of money they want to get in the 3% scenario is this top black line. And you can see it is about, starting at 1.25 billion in 2023 and rising to $2 billion by 2035 on a nice little ramp. The line that corresponds to the black line in terms of the money that goes to the projects is the blue line. And the blue line assumes a 30% fraction for projects. So that means 70% is for other stuff. I don't remember if the report goes into all the details on that. Then they have a less favorable scenario. If the funding agencies don't want to go to 3%, they're going to offer them 2%. And then if they get the lesser money, well, then the amount of money for the projects is the red line, and that goes down a little bit. I don't know. You can argue with how they do this, the way they couch it, the way they're kind of playing the game of funding. I know all big organizations do this kind of thing. Now, my prediction is that once we get into the next era, the high technology industry will be a major source of funding for research and development. And the reason is because once we get into the next era and point charge theory, it's essentially like having the source code to nature. We know exactly how it works. We know all the math. I extracted this section from the report, and I thought we should go through it because it's talking about investing in initiatives aimed at developing the workforce, broadening engagement, and supporting ethical conduct in the field. And they say this commitment nurtures an advanced technological workforce, not only for particle physics, but for the nation as a whole. First of all, developing the workforce, there's quite a few physicists and cosmologists these days. The grad students, post-grads, and the professionals in this field are paid very poorly. In terms of ethical conduct, there's been a lot written about plagiarized papers, modified data or cherry-picked data. And on the people side, of course, there's a lot of issues with bullying from the people in the hierarchy of these fields that are in power. And there's also been quite a bit of sexual harassment, discrimination against women. These are all real problems for the field. It's not really clear to me that they're being solved. So you can read through this at your leisure. I would recommend downloading the whole report, but you can also pause the video and look at it. I want to call out this part of the report with the green arrow. It says, funding agencies should strategically increase support for research scientists, research hardware and software engineers, technicians, and other professionals at universities. So you have to ask yourself, what does that mean? Do they just want more people, or do they actually want to increase the compensation for the people in this field that are really struggling to get by? They love academics, they love teaching, they love learning, being at the forefront of knowledge, or what they think is the forefront of knowledge. But, like I said before, that the compensation's really poor. I don't know. We'll get into some more things here in this report. I don't get the feeling they're talking about increasing compensation for all the bright people in these fields. I think they're looking to scrape and claw to get more done with their projects, and they will take advantage of people if they can. This section of text that I've highlighted says, the experiments needed to address the most profound questions of our field often require resources and cooperation at a global scale and can take more than a decade to design and build. That's true. The way particle physics has approached their solution to nature, things are very costly and very time-consuming, and progress has been extremely slow. In fact, many people will say there hasn't been major progress in 50 years. Yeah, we spent billions of dollars on the CERN particle collider, and it confirmed the Higgs boson, but the Higgs boson was suggested in the early 1960s, and the math for it was laid down then. So, when you really look at what particle physics has produced in the last 50 years, I mean, there's some good throw-offs, but it's really in a crisis, and some people in the field have their head in the sand, and they don't want to acknowledge that the field is in crisis. This section says, particle physics studies the smallest constituents of our vast and complex universe. At such small scales, the fundamental principles of quantum physics prevail. Remarkably, the entire observable universe, now billions of light years across, was once small enough to be quantum in nature. Its quantum history is imprinted on its large-scale structure. Well, some of that's wrong. As far as I can tell, using point charge theory, there was no one-time Big Bang. I think that what has happened here is that scientists have totally misunderstood the concept of expansion of space-time. They don't understand it because they're on the wrong ontology. And it turns out that space-time is not just a pure geometry. In fact, space-time is made of structures or assemblies made out of point charges. They're extremely tiny, they permeate everything, and they are scalable. They can inflate like a balloon, and then when they get to a certain size, they expand from there. So the space-time structures are the things expanding, not just some geometrical view of a vacuum, with Einstein's equations. That's the wrong way to look at it. So you have to ask yourself, well, where does all this space-time come from? The fresh space-time that's being created. And, well, it's not hard to figure out. It's coming from within galaxies. And it's most likely coming from very high energy events. So supermassive black holes, if they meet the right conditions, would presumably emit space-time. And I can think of two ways they can do that. One way would be at the poles of a spinning black hole, we get a vortex on either pole called frame dragging. But what's happening here is the space-time assemblies are so thick close to the black hole that it's really essentially dragging around this soup of space-time, creating a vortex. And it's possible that the extremely tiny, dense point charges inside the black hole can escape through the poles and be part of those enormous jets that fly out of supermassive black holes occasionally. There's another possibility. I mean, remember, current science is really tenuously balanced on an incorrect understanding of photons. It doesn't understand that photons are assemblies made out of point charges. A lot of the math on black holes is based on, could photons escape a black hole? Okay, fine. But since they don't know that there's an assembly architecture of point charges and that space-time is made out of assemblies, nobody has considered whether space-time can just escape right out of a black hole. I mean, it's extremely lightly interacting. We know it's going to be the medium through which we understand gravity. But, we're passing right through space-time, and it's flowing right through us, far more than neutrinos are. And, there's a common expression, like some millions of neutrinos pass through your thumb in the time it takes to say this sentence or something. I don't know, you can look up the actual number, but there's far more space-time that you're passing through as well. I think it's very possible space-time may just be able to flow straight out of a black hole. I mean, it's created, it's extremely tiny, and it's nearly invisible because of superposition and because of the frequencies and speeds involved of the point charges in space-time. Yeah, they're at an extremely tiny radius, but they're also at very, very high frequencies near the Planck scale, at least when they start out. And so you're going to have these effects that just mean it's extremely tiny and it's nearly non-interacting. It's superimposed in a way that it just doesn't really hardly interact at all. So it may be able to seep right out of the outer surface of a black hole, and essentially a black hole would just then be creating all kinds of new space-time. That new space-time would then interact over time. It's available for reactions with other particles, and it can contribute to those reactions, can be repurposed into what we call standard model particles. When you look at this first paragraph that I've got highlighted in yellow, this talk about an expanding universe is wrong. The talk about a universe that's 13.8 billion years old is wrong. In point charge theory, the basis of the universe is a Euclidean void in time and space with no known end in physical distance. Also, no known origin in time, no beginning that would be known, and no predicted end. There's no bounces, crunches, not in terms of space itself. It's just out there. Now, all the particles in a galaxy and from ones that enter a galaxy, they're going through their own life cycle. They may get tied up in a planet or a meteor or a sun or so forth. But there's this general trend of particles moving towards the black hole where they could join a black hole and their energy could become consumed by that black hole. And then those point charges that are forming our standard model assemblies can be recycled. And then as they're recycled, they can come out in the form of new space-time. That's an interesting way to think about it, but what it means is we have kind of a quasi-steady state universe, and so there would be no age known, and that's important. So it says, past successes in particle physics have revolutionized our understanding of the universe and prompted a new set of questions. And then later on it says, we stand on the threshold of harnessing their full potential. So if you notice, some of the words in this paragraph are trying to portray or spin the situation. It says, particle physics has revolutionized our understanding. A lot of this was done quite a while ago. In the 1970s is when the standard model really got solidified. And since then, not a whole lot of major progress in terms of the fundamentals in particle physics. They're stuck. They have to kind of perfume the field here by saying, things like it's revolutionized our understanding of the universe, it's prompted new questions, we're on the threshold. Ooh, does that mean, we're close? We could harness the full potential. What does that mean? That sounds really good. I want to, increase your budget. I found this report to have quite a few words that were spin-oriented words, and I'm going to just say I think that's something that really doesn't belong in a report like this. It's not scientific to try to spin this. They should be honest about the situation. They're in a crisis. Let's just acknowledge that it's a crisis, but we also want to make progress. So this graphic appears in the report, and I thought it was just kind of not only a cool diagram, but it kind of lays out some of the major things they're looking at. So on the left side, they have decipher the quantum realm, and they want to elucidate the mysteries of neutrinos. Neutrinos are also an assembly made of point charges. One of the things we know about neutrinos is that their mass oscillates, and it turns out that's probably because the assembly is semi-stable. It's kind of wobbling. And so as it wobbles, it kind of affects the superposition of the point charges in the neutrino. And because of this wobbling, the superposition will change. Therefore, when it wobbles, it may reveal some of the internal energy that has been shielded in the generation 2, or even in the case of the generation 3 neutrinos. So, you can imagine this neutrino is flying through space with, it's probably got 12 point charges in it, is what I think. And because the structure is not entirely stable, it wobbles, and that reveals energy, and therefore that energy looks like mass to us, and so we see this oscillation in mass. Now, if physicists understood the point charge architecture of nature, they would already know about neutrinos, and they would already be able to just simulate them. They could know all kinds of things. No need to build huge experiments all over the world and spend all kinds of money researching neutrinos when you've got the source code in nature in hand, and you can just simulate what will happen. That one is kind of not a good use of money. The next one is to reveal the secrets of the Higgs boson. They want to understand more about it rather than just confirming it. They want to try to dig into what is a Higgs boson. And like I said before, I think the Higgs boson is related to the space-time assemblies. So again, if they understood the point charge architecture, they would probably have a lot more understanding of the Higgs boson. Let me go to the right section. It says illuminate the hidden universe. So that's the cosmology section. And determine the nature of dark matter. Well, we were just kind of talking about that a little bit. The way these assembly architectures work for the Standard Model is that there are components inside the assembly. There are orbiting binaries of point charge pairs, a positive and negative, and the orbiting binaries in the inside, their energy is pretty much shielded. You can't really tell it's there unless you were to break apart the particle, and then you see it form, the higher energy particles after that. Dark matter is pretty easy to understand if you know the point charge architecture, and the same is true for dark energy. So again, that's probably something we shouldn't be spending a whole lot of money on. We should just get on with the point charge architecture and research it from there. It would be a lot more productive, and it would be less expensive. The other area in that section is understanding what drives cosmic evolution. Now that category is pretty wide. It could go in terms of understanding inflation and expansion, which are both real. They occur in the point charge architecture, just not the way scientists think about it now. When new space-time is emitted by a high-energy object in a galaxy, probably the supermassive black hole, maybe some of the other black holes, maybe some huge collisions or whatever, mergers. When that new space-time is emitted, it is going to inflate very quickly as it starts giving off energy. And as it escapes the black hole, it can react, it can spread energy to other assemblies. We will have inflation and expansion, just not like a one-time inflation and a gradual expansion. It's not like that. It's happening all over. In fact, every particle in the universe is constantly redshifting to some degree. And when particles redshift, that means they're giving off energy. And the way this scalable architecture works is that the size of the core of the particle changes with energy. The more energy it has, the smaller it gets, and the less energy it has, the bigger it gets. And that's how you get inflation and expansion. Now, if you look at the overlap of these two areas, that's the middle column here, explore new paradigms in physics. They're trying to figure out, how can we join cosmology and particle physics? They're really not joined at all. General relativity and quantum theory are incompatible. There might be a few strands that they can try to stretch across the gulf, but mathematically they don't play together. Also, you should know that general relativity doesn't have a foundation in nature. It's just It's just a geometry and then pure math up from there with no explanation of how we got there. These scientists truly believe that space-time is stretchy and curvy from nothing else other than just being space-time. Like a vacuum is what they think of it as a nothing. But in reality, it's these enormous collections of tiny point charge assemblies that permeate everything everywhere. When they say they're searching for direct evidence of new particles, that makes me queasy because they'll spend a lot of money trying to make things like pentaquarks or other exotic particles. But when you have a point charge architecture, you can smash a bunch of stuff together and yeah, some couple of point charges may come out of that and it may look like a new particle, but a lot of these are highly unstable and they go away. So, it'd be like crashing two cars together and two pieces fly off together and you say, oh, that's a new particle. No, it's just two pieces that flew off of that big collision and interacted with each other a little bit while they were flying away. It's just not that interesting. And also, we'll be able to simulate that. And not only will we be able to simulate it, we'll be able to simulate it with provenance. We'll be able to track every point charge in a reaction when we simulate. So we'll be able to understand exactly how these things work, why they produce different results sometimes. We'll be able to figure that all out. This slide shows another section of text which has, again, some of these spin type words. I just want to read a few of these things to you. You can read the whole paragraphs if you want, but one part here about experiments ensures a continuous stream of groundbreaking research with exceptional discovery potential. Not discoveries, but discovery potential. Think about that. It goes on to use words like excellent science. I don't know, is it excellent science when these fields missed the architecture of nature 125 years ago during the classical to quantum transition? Is that excellent science? I mean, at the time, maybe they just weren't creative enough to figure out the architecture, but it's been 125 years and it's been extremely difficult in these fields. And there's a lot of paradox and open questions, huge open questions. No other science has this much of a mess on its hands. Then it goes on to say, talk about things that play a crucial role. They're going to begin to unlock the secrets of the Higgs boson, which is there's a decades-long program to reveal the mysteries of elusive neutrinos. And there's just some more things to just show you how far off the fields are. They're going to study the oldest light from the beginning of the universe. Well, if the universe has no beginning or end, I'm not really even sure what that means. If there's no Big Bang, there's no beginning of the universe. It's just always been here. It's always been kind of evolving over time. But there's no beginning of the universe 13.8 billion years ago. Now, there are sources of light far away, and there are sources that we can detect the light, and that would be the oldest light we could detect. But that's just a proximity thing. If they're right about the light we are seeing has been traveling for 13.8 billion years, it's not because it came from a Big Bang. It's because that's just the light that can reach us, and we can sense it with our experimental equipment. Nothing really special there. Then they talk about a dark matter experiment will probe the enigmatic nature of dark matter, which makes up a significant portion of the universe's mass and energy, and has been one of the most enduring mysteries in modern physics. Shouldn't have been a mystery. We should have understood this over 100 years ago. The core of every particle is 3 point charge binaries at vastly different energy scales. I call that core a Noether core, after Emmy Noether, for reasons that will become clear later in this series. And it's excellent at shielding the internal energies. In fact, if you take out the outer lower energy binary, now you have the generation 2 particle and you're revealing some dark matter and dark energy. If you take off the lowest energy binary and the medium energy binary, now you have the generation 3 fermion particles and you're revealing the highest energy and more matter. Those are going to be things that go into figuring out what we call the missing or undetected dark matter and dark energy. Now, there may be also new findings in terms of what's going on inside of a black hole. How many point charges in there and how much energy, and has that ever been accounted for? No, probably not. So that's another aspect that I think they could be able to theoretically predict, probably never be able to measure the inside of a black hole though, that's for sure. CERN is a 100 giga-electron volt particle collider. So one of the goals of the physics community is to get to a 10 tera-electron volt center of momentum collider. This panel is recommending moving forward on that, or at least exploring it. And they want to search for direct evidence and quantum imprints of new physics at unprecedented energies. Turning this concept into a cost-effective, realistic collider design demands that we aggressively develop multiple innovative accelerator and detector technologies. This process will establish whether a proton, electron, or muon accelerator is the optimal path to our goal. Again, you don't need this. The existing colliders we have are more than adequate to become test machines and verification machines for the new era. In fact, they may be way too expensive as test and verification machines. With the knowledge of essentially the source code of nature, we will be able to simulate precisely and discover things so quickly that we may find far less expensive, more expedient ways to test the theories. The impact of the more constrained budget scenario. Now remember, that's 2% on top of, what did I say, $8 billion. So we're either asking for 2% or 3%, but the constrained scenario is 2%. So it says the impact of the more constrained budget scenario is severe. Really? Severe? It forces the US to cede leadership in many initiatives to other regions of the world and reduces investments in workforce and future technologies to critical levels. Wow. That's a pretty big, kind of bad scenario that they're painting there. Is that really true? I don't think so. Reduces investments in workforce. Remember, I talked before about how they don't really invest in the workforce, except maybe getting more people. They certainly aren't investing in compensation for these people, or perks, or benefits. That's not happening. Specifically, the G3 dark matter exploration would be relocated elsewhere, and elements of DUNE would be descoped or delayed. This limiting of DUNE's physics reach would negatively impact the reputation of the US as an international host, and more limited contributions to an offshore Higgs factory would tarnish our standing as a partner for future global facilities. So again, they're basically saying if we get 2% instead of 3%, we're going to have to kill some projects, and we're going to be negatively impacted. It's going to hurt our reputation. We're going to make limited contributions. The Higgs factory is going to be offshore, and our standing is going to be tarnished. Okay, a lot of spin words there. When we're talking about 2% versus 3% on an $8 billion budget. Let me read this one. Curiosity-driven research is at the core of particle physics, a field of science in which we study the building blocks of the subatomic world. In examining these point-like particles and their actions, we decipher the quantum realm. Well, they want to decipher the quantum realm, but they don't even really know what the quantum is yet. They fudge here by calling the particles they're working with in the standard model point-like particles because they don't know the internals. But they do know that there's a bunch of internals because they measure things that they can't account for that wouldn't happen in true geometric point charges. By studying the very small and the very large, realms that are beyond the limits of human perception, we expand our understanding of the world around us and begin to grasp our place in the cosmos. Going beyond phenomena that we can probe using current experiments, we can use theoretical principles to test our current physics understanding and predict new particles and new phenomena. In this way, we explore new paradigms in physics. No, that's not true. They're not really getting into new paradigms. I mean, you could look at the James Webb Space Telescope and, some of the initial observations. Now, I know it's early days for the James Webb, and a lot of things has to be checked and double checked and triple checked, and a lot of science has to be done. But what you can already see happening is they're finding things that shouldn't be there when they look out into what they call the oldest light, which is the oldest light, but it's not from the beginning of the universe. It's just old light. Now the universe is, as I said, it's going to go on forever in every direction. There's no Big Bang. There was no one-time initiation of the universe that we know of. And so you kind of want to ask the question, if we can actually see light, from 13.8 billion years away in kind of a spherical shape, isn't that enough to explore? If the universe is isotropic and uniform and the same physics everywhere, and there was no Big Bang, how much do we really need to explore? I mean, we're going to get the idea, right? I mean, yeah, there might be some long-term evolution in the way the universe kind of changes over time. Or it might just be that it's just a big dynamical geometry, and all these things that we see are what happens, the variety of things that can be created. So this slide talks about a paragraph from the report that mentions the funding agencies are the Department of Energy and the National Science Foundation. These agencies have nurtured a world-class scientific enterprise, from the discovery of the Higgs boson and the revelation of the neutrino masses to the stunning realization that the expansion of the universe is now accelerating. This effort has revolutionized our understanding of how the universe works. With each new insight into the universe, scientific exploration encounters escalating challenges. The tools and technologies required to meet those challenges become increasingly sophisticated. Okay, well, the reason you're having escalating challenges is because you're on the wrong ontology, okay? As I've said, there's a straightforward, parsimonious solution to nature, and it was missed around 1900. They had many opportunities between 1900 and 1925, 27, when kind of general relativity and quantum theory were starting to solidify. They missed it. And nobody since then has gone back and looked, even though they're in a crisis. The highlight in this section is, let me read it, the muon G2 experiment measuring the anomalous magnetic moment of the muon has observed a discrepancy between the measured value and the value predicted by the standard model of particle physics, a result that spurs further theoretical developments. Okay, so the muon is the second generation of the electron. And it's a higher energy particle, but it has relatively short lifetime, a little longer than other short-lived generation 2 or generation 3 particles in the standard model. And remember before we talked about how sometimes they say these are point-like particles, but now they're saying here that there's this anomalous magnetic moment. Well, obviously there's something inside the muon, or something it's doing. It's got some reductionist constituency that is causing this. Yet they'll still use words like a point-like particle, which it's not. Now, they'll also call these things excitations in a field. In fact, that's their main theory, is that every particle in the standard model is just citation in the field for that particle. So every particle has its own field. And when you go throughout space, three-dimensional space, you can have little excitations. Oh, that's an electron, right? Oh, here's another electron in the same field, right? But if you want to look for neutrinos, well, then there's an excitation here and an excitation here. And those are neutrinos. That's really how they think about it. But they know that when these things are in reactions, that, you know, the particles that go into a reaction, some might come out whole, but then other particles may come out. They may reconfigure into different particles. But yet we know that when we have multiple particles going into a reaction, they may survive the reaction, but also they may not, and they may decompose and create new particles. Scientists don't understand how that works. And yet they've worked it out with their field theory so that they can convert between particles in one field can somehow react with particles in another field and create a third particle in a different field. So that's fine. You know, their math, I'm sure their math works. It's been well tested, but it's, as I've said multiple times, it's at the wrong ontological level, and it's way too complicated for what is needed. And on this slide, you know, the Standard Model is a remarkable achievement. Yeah, it was. Considering they're on the wrong ontology, getting as far as they did by the 1970s to figure out the Standard Model, it is remarkable. But that's kind of also like taking the wrong path on a hike, and you end up, you know, going off for 70 years hiking through some wasteland to make progress when you could have figured everything out in a couple years back at around 1900. So I'm not sure I would be patting myself on the back for this. No, they don't know about the point charge architecture yet. In fact, they're very loath to believe it might exist. They won't even entertain the concept because they think they're the smartest people on the planet. They've got experimental data that confirms quantum theory to extreme levels of precision. And with those things, they feel like they're kind of on top of the world. They're chasing down the source of nature. And a lot of the people in the field don't really understand they're even in a crisis. They think they're applying the scientific method properly, and they think there's nothing wrong with the scientific method. But there is. Did you know that the scientific method has no proactive measures to detect a crisis in a field? No proactive methodology to suggest that if there is a crisis in the field, we should go back and examine the history in that field and look for where there might have been an error. And of course, if you have a crisis right now and the theories are general relativity and quantum theory and they're not merged and neither has a foundation, you're going to have to go back before both of those to find the error. You know, so Einstein first came up with general relativity around 1915. Then we had quantum mechanics coming a few years later. You know, and by 1927 at the Solvay conference, there was kind of a consensus view with a lot of bullying and pressure on certain people to, you know, everybody get behind general relativity and quantum theory and just shut up and calculate. And that was a really bad idea. You know, and so I think there's a major flaw in the scientific method in that, yeah, maybe over a couple year period, it might find mistakes in lesser theories and so forth. But when there's a major ontological problem, and here's an example, 125 years on the wrong ontologies, and ontologies that are incredibly complicated and difficult to make progress on, and where to make progress, they have to basically throw away a lot of their narrative. I mean, it's really going to be difficult for them ever to find the true solution in nature that way. And the scientific method offers them no help for that. That's a problem. It's a big problem. They also talk about understanding the origin of particle mass. Scientists can't tell you what mass really is. So Einstein said we can convert mass and energy either direction. But what isn't understood is that there's concealed energy within the standard model particles. That's where the higher energy particles, like in the fermions, the generation 2 and generation 3, that energy is essentially inside the generation 1 particles, but it's shielded by superposition, and so we can't see it. So you have the observable energy, which converts to mass, and then you have the total energy, which is the true total absolute energy. And then if you take the total minus the observable energy, that's the concealed or superimposed energy that's hidden. When we can figure out how to harness that, there's a lot of energy inside of every particle that we have no idea is even there now. This section talks about the Higgs boson. The first section I want to get to says, the existence of the Higgs raises questions about why it is frozen in the universe, imbued in a field that gives mass to all elementary particles. Well, again, if you understand the point charge architecture of nature, space-time, which seems closely related to the Higgs, is actually made of point charge assemblies that are extremely stealthy. They're very tiny, they permeate everything. When we say they give mass to other particles, that's because the other particles are essentially, in a way, surrounded and permeated by the space-time, and when a standard model particle tries to move through it, it is going to have some slight interaction with the space-time, and then that resistance to movement is what we call mass. It says, the Large Hadron Colliders collide high-energy beams of protons to investigate their fundamental structure and produce particles of higher masses. These scientists have no idea what a proton is made of, really. They think a proton is an up quark, a down quark, and an up quark. Well, what's an up quark? They don't know. It's a point-like particle, has some internal characteristics we don't quite understand it. There's these things called gluons that are evolved and so forth. Well, an up quark is one of these Noether cores, which is the 3 nested binaries, which of course would have 6 polar regions. And in the 6 polar regions, we can stick other lower energy point charges. So if the point charges have a magnitude equal to 1/6 of the electron, then we can make fractional charged particles like the quarks. And you can easily do the math of how many negative point charges and how many positive point charges you need to make an up quark. You can look for anti-up quarks by changing out the Noether core, so it's got a slightly different formulation. You can spin the Noether core left or right. If you really want to understand a proton, you're going to have to understand the point charge architecture. So you've got 2 up quarks. Each up quark has 12 point charges, and a down quark has 12 point charges. So a proton has 36 point charges, all kind of at different energy scales, creating this very stable assembly. But it's also changing all the time, right? So we have these things called gluons, which are really just the interactions between the internal binaries of these 3 Noether cores in the 3 quarks. And, so that's a proton. A neutron also has 36 point charges, but it's formulated slightly differently. It's a down quark, an up quark, and a down quark. And again, it's just 3 of these assemblies which have 12 point charges and these personality charges in the poles of the 3 binaries of each quark. And so if you have a down, an up, and a down, that makes a neutron. When they collide protons, you accelerate these protons in the colliders, and then fly them towards each other at very high speeds, and they manage every once in a while to actually have a collision or a reaction, essentially, is what's happening. So this group of 36-point charges is flying, and then this group of 36-point charges, and so boom, they strike each other. Now remember, they're also totally permeated by space-time assemblies, which have tons of point charges because they're so dense. And what you'll see is the space-time will contribute point charges to some of these reactions. So you might see, if you actually counted the point charges coming out of the reactions, sometimes you'll see more come out of the reaction than went in terms of just the standard model particles. And the ones that are coming out were contributed by the space-time assemblies. These studies will eventually be limited by the challenges of using proton beams, which are composite objects made of quarks and gluons. We talked about that. The next step is to use electron and positron beams to construct a Higgs factory, which would allow precision measurements of the Higgs boson properties and searches for exotic decays, possibly into dark matter. So they're going to totally change the type of collision. They don't have much experience with colliding electrons and muons. They have done some. But again, like if they would just get on board with the point charge architecture, they could simulate all this. They don't need to build these expensive colliders and wait these inordinate amounts of time to make progress. Okay, let's switch into cosmology. Let me read this under the Illuminate the Hidden Universe section. When we look backward in cosmic time, we see a universe very different from the one we know today. I think James Webb Space Telescope is showing that there's quite a few things back 13.8 billion years ago that shouldn't be there according to our standard model of cosmology, lambda CDM. And some of those things are so large in terms of galaxies or black holes that they're trying to figure out what it means. Like, does it mean LCDM is irretrievably broken, or does it just mean we have to add some shims and kind of do some curve fitting to come up with mechanisms so that galaxies can grow super fast or black holes can grow super fast, so that we can explain how they're there when the universe just started, right, in their ontology. But their ontology is wrong, so this is all nonsense. You would expect to find those things out there in a quasi-steady state universe. The universe has evolved from early moments of rapid expansion, or also called cosmic inflation, which left behind the seeds of its future structure, to intermediate periods dominated by radiation, potentially including unknown light particle species and dark matter, to our current epoch of accelerated expansion driven by an unknown component we call dark energy. Okay, well, yeah, but we can explain dark energy and dark matter by looking at the point charge architecture. There's a lot of it just inside the particles of standard matter, inside the particles of space-time. And I would hazard a guess that there's probably more energy stored inside of black holes than we realize. There's parts of the narrative that they have that go along with the Big Bang and this, the origin of the universe story that do happen, but they happen at a galaxy local level, right? So the recycling mechanism in the universe is just done at the galaxy. So energetic standard model is attracted to each other by gravity. It eventually forms, groups of standard model particles which turn into comets, meteors, planets, stars, neutron stars, small black holes, large black holes, supermassive black holes, right? Eventually you get to the point where the energy is so high inside these objects like the black holes, the photon assembly can't get out. I mean, maybe it's not even formed yet at that point, but I think the only thing that could get out would be the assemblies of space-time, because they're just so stealthy. They're virtually non-interactive. They should be able to come right out. So there's been this theory called weakly interacting massive particles that's been around for several decades. It's kind of an off-again, on-again theory. I don't understand this theory, but I do wonder if it's related to the shielded parts inside of the standard model particles that we reveal with the point charge architecture. So if we look at the Noether core, with its 3 nested binaries at vastly different energies, vastly different radii, vastly different frequencies, the shielded energy of the internal 2 binaries, it may correspond to these weakly interacting massive particles. The other thing they could correspond to is the space-time assemblies, because they're just entirely shielded, but the energy in those internal binaries of the space-time assembly are also very high energy. It'd be wonderful if we could tap into it and control it. We have an infinite source of energy. We could potentially someday just use space-time as a raw ingredient to make anything we want, or to power anything we want. But that's probably pretty far off, but not that far off if you have the source code of nature. Here's one that really bothers me. Particle physics has a long proven record of creating new technologies that have revolutionized our daily experience, such as the World Wide Web and life-saving medical applications, from cancer treatment to medical imaging, derived from particle accelerator and detector technologies. The tools developed for particle physics research also impact society through their adoption by other scientific fields. Applications in chemistry and material science, for instance, have led to innovations in drug discovery and the design and realization of novel materials. So physicists kind of like to hang their hat on this, oh, because of us, we have the World Wide Web, look how great that is. So even if we're making slow progress, we're still throwing off fantastic technologies. No, absolutely not. We've got to have accountability. The job we're asking physicists to do is to find the solution to nature. It's wonderful if they throw off other technologies, impactful technologies. That's fantastic. But if they're not solving their core assignment, the problem we assign to them, then it's a failure. I mean, that should be clear. And for the communities here to tout things like the World Wide Web and drug discovery and medical imaging, yeah, that's all great stuff, but that's not what we asked them to do. It's great that they generated that, thank you, but please make progress on what we asked you to do. Now, as I've said over and over again, they really can't make progress because they're on the wrong ontologies. I found a lot more paragraphs that, repeat some of the things we've covered so far. I'm not going to read every one of them. I think I've made the major arguments. But I want to turn now to this particular slide on people issues. So it's called Recruiting, Training, and Retaining. And let's read what they say. To nurture this workforce, it is imperative to recruit individuals with a broad range of backgrounds and provide them with the skills and resources needed to advance the field. To retain this workforce, we must provide career pathways and an environment that encourages and rewards exemplary work. Okay, we already talked about compensation's really bad. A lot of the physicists in academia complain, especially the postgrads. There aren't many professorship jobs. Tenure is extremely difficult to get and also seems to be fading as a mechanism. And when they talk about career pathways, I think the most dominant career pathway is to leave the field. Some particle physics trained researchers will chart career paths in other areas of academia, as well as in government and industry. Their multidimensional and technical expertise in areas such as accelerators, quantum sensors, and AI/ML, artificial intelligence and machine learning, will make them sought after for jobs in quantum computing, medical physics, and other data-rich environments. That's true. There are quite a few physicists who go into other careers, but that wasn't their first choice. They studied this, and they would really like to use that knowledge that they gained, the expertise and the skills, in the field of physics or cosmology or astronomy, right? Astrophysics. It's disingenuous for this report to talk about all the pathways we're providing for the people who are exiting the field. why don't they say something like, you know what, this year we want a 2% increase in funding so we can right-size the compensation for our people. That would be a good thing to do, right? Here's the next slide on people issues. This one is a paragraph on retaining. People are our most precious resource. They don't act like it. They sure don't act like it. Not in compensation, not in environment for some of the people in the field. We haven't yet talked about the hierarchy in these fields where there are certain people in power, the professors, the department heads, the principal investigators on large projects, and you really have to go along to get along. These fields do not permit much dissent at all. They don't really want to have new ideas. They seem to want to continue to bang their head on these ontologies, which are extremely difficult and which are yielding virtually no progress. Saying that people are their most precious resource and treating them this way doesn't make a lot of sense to me. This infrastructure must ensure accessibility, including living wages and sufficient support for those with family and caregiver responsibilities. Studies of the work climate of the field, informed by experts in sociology and organizational psychology, can allow us to identify barriers to participation and engage our progress. Well, they could just talk to their people too. I mean, I think the people will tell them what the problems are. I mean, I can see it just by reading social media. There are quite a few scientists who are open about these problems. And then what do they mean by living wages? Living wages, really? Like some of the sharpest people on planet Earth are getting living wages when people in computer science are making $200,000, $300,000 a year in, what is it, 2024 now, with a bachelor's degree? And people in AI, I think some of them are making $500K or more. It's just a worker bee. So paying PhD physicists living wages doesn't make a lot of sense to me. And I don't know how academia got so upside down on compensation. Why should our academia pay so poorly? I mean, I understand they have to go get funding and, you know, everything's run by funding. It's hard to get funding, but I don't know. I just don't understand how it got to this terrible position where, you know, people can't afford, you know, good living situation. They're having problems with family care. I don't know. It's just really a mess, if you ask me. But yet they kind of paper all this over or give it lip service in this paragraph as if they don't know or understand what the problems are. This page talks about the relationship between the fields of physics and cosmology and the physicists and cosmologists and their relationship with the public. It mentions the fact that the public essentially fund the science. So it says, it is the duty of particle physics community to recognize the value of public engagement. In addition, recognition of the value of public engagement is essential to building the necessary culture. Well, they have this thing called outreach. There are quite a few scientists who do a really great job writing articles for the general public or creating educational videos that they make available on YouTube or making sure talks are recorded. But let's be clear, you know, outreach, I don't know, when I think of outreach, to me it's like one hand reaching to another hand and kind of a two-way relationship. So I don't think outreach is the right word. This is more like a diode. It's like a one-way flow of information. If you've ever tried to talk to one of these people, you'll find out that you're allowed to be silent Or you are allowed to ask questions, but not too deep of a question, and you're never allowed to express an idea, okay? I think the fastest thing in the universe is a physicist running away from some member of the public expressing an idea. They get so uncomfortable when you try to talk to them about an idea. Now, I mean, I kind of understand that. Probably 99.999% of the ideas they get hit up with from the public are nonsense. But another way to look at it is that these are people who kind of adore the scientists, they follow them, they see patterns or figments of patterns when they're trying to understand this, and they come up with ideas that are often, very non-reality based. The scientists apparently have never taken any education about how to professionally deal with the situation. A lot of them will get hostile, and they'll be very hostile to the public that comes bearing gift ideas. It's a really strange behavior, if you ask me. Now, they're getting peppered whenever they give a talk. They're getting people sending them email constantly or responding to them on Twitter or sending them direct messages. I understand all that. That's probably a pain. But what's so hard with just saying to people, wow, it's so wonderful that you're having ideas. Great, keep working on them. I'm currently engaged on my own set of ideas with my colleagues, and I just don't have time to get engaged with yours. But I do encourage you to continue to work on your own ideas. I mean, there's ways to do this that are professional. They don't have to be mean to people bearing ideas. They don't have to call them names. They don't have to suggest that they're mentally incompetent. This is the norm in physics, to do this. It kind of blows my mind that they act this way. I spent 40 years working in industry, and I had all kinds of executives and customers coming constantly with ideas that made no sense. I couldn't be mean to them. Are you kidding? Those are the customers. Those are the people paying the bill. You have to find a way to be professional, thank them. But you gotta kind of just not lash out at those people. They're trying to help. They're trying to help you improve your own product, or they're trying to help you make progress. So here's my recap and some recommendations. I think the fields of particle physics and cosmology are lost. They are lost because they chose ontologies that are at too high of a level. Their math works, their experiments match their math. That's fine, and that's good. But there's so many far easier ways to get this done. Therefore, I would say that these fields require a teardown and a rebuild from this new foundation in the point charge era. Now, what does that mean in terms of a teardown? I don't know. How do you tear down an ontology, an entrenched ontology, or entrenched ontologies, plural? It's going to be difficult. They work. So to some extent, they all work. And what we have, we can continue to use. But we need to get people focused on building up the new ontology. So that means doing all the science and math to establish how exactly this new architecture works as we continue to build out assemblies of point charges, and then how do they react, what does the provenance tell us, then start getting into how can we manipulate and control these things, how can we create reactions we haven't seen before and then go experimentally verify them, how can we leverage the hidden energy that's in these particles and also in space-time. There's just a tremendous amount of important work that needs to get done that's not being done right now. And that all needs to happen. Now, what do you do about the people in the field? The senior people? Is there going to be any accountability for them for Yeah, they didn't like miss, they weren't responsible for the original miss of the architecture back around 1900. That's not their fault. But they have worked in this field for decades, and yet nobody's been like honest enough with themselves to say, hey, we got a major problem here. We need to really invest some serious funding into going back and figuring out, did we make a mistake? Did we miss something? Where is that, and how can we find it? Now, it turns out I think I found it. And I'm trying to give it to physicists and cosmologists for the last 5 years, but they won't even listen. So we'll just teach everyday normal people, because it's actually pretty simple, and they'll eventually catch on. Now, I think that this transition period from the current era to the next era is going to be difficult for the people in the field. If you think back in history, there was this thing called epicycles, and that was when early scientists thought that our solar system all orbited around Earth in some pattern. And so to create the math that made everything look like it orbited around Earth, then you had planets doing motions like this around Earth, over large places, over the solar system. Along came an important scientist who said, no, I think everything's rotating around the sun, because if we go rotate everything around the sun, then everything's just kind of a circle, or an ellipse, going around the sun. It makes a lot more sense than these loop-de-loops. Well, that was called epicycles, and that was a paradigm change. We totally changed the narrative of the observations in the math. So we had observations that matched math, but the wrong ontology. And then we got onto a far improved ontology with everything in the solar system kind of orbiting around the central star, or the sun in our case. So what we have here is far worse than the epicycle debacle. We've got 125 years of really bright people, huge numbers of scientists working on the wrong ontology. Now, here's some good news. The fields are going to be a lot more productive once they get onto the new ontology. The future pathways for research and technology will be abundantly clear. I mean, once you have the source code to nature and you can simulate everything, I think it's sky is the limit on technology, because we'll be able to understand exactly what's causing the current limits in technology, and we'll be able to experiment in simulation with ways to get around that, or just use the simulation to find entirely new mechanisms that can implement important technologies or release energy from particles. And once we can harness these things, the amount of funding coming into the field from the high-tech sectors of research and development will be amazing. It'll be just absolutely amazing. And I do say that the existing facilities and experiments in high-energy physics and particle physics, I don't think they'll really be that useful going forward. I think they're bloated, expensive projects with too many people for what they're producing. If anything, maybe they could be repurposed as test and verification systems for a while, but I think eventually just shut them down and phase them out. There's probably going to be far superior ways to do the test and verification than with these expensive, large-scale experiments. And then again, I just want to stress, I do think that technology investors will come in, and it'll be a good thing for people in the field. If they want to have an opportunity in breaking new ground, leading edge research and development in a non-academic setting, I think there will be plenty of opportunity for that. If they want to continue in academia, there'd be plenty of opportunity for that now too, because they can do research and development. And I think, maybe industry will be more forthcoming with funding for academics. I mean, I hope they would. And that could possibly lead to fixing some of these problems that all these people have in the field in terms of compensation. And I think that would be a good thing as well. Thanks.